Okay. Well, thank you, Paulina. So I guess for um, people who don't know me, I was doing a PhD in Universitat Pompeu Fabra (UPF) in the music technology group, and I just defended the thesis, the final thesis in September. And before doing that, I sort of joined a company called VoiceMode back in March, and I was sort of doing both things at the same time, which I would really not recommend to anybody else, but thankfully things worked out. Um, anyway, so in this presentation, I'll just describe some of the work I did during the PhD, and then how that is sort of being applied in the industry, in the job that I'm working in, and also what sort of work we are doing here, and hopefully what we want to do in the future. So the thesis I presented was titled Neural Networks for Singing Voice Processing in Polyphonic Music Signals. And it was carried out from 2017 to 2021 under Dr. Emilia Gomez. Um, the idea behind the thesis was basically source separation using synthesis for contemporary popular music, in which case we synthesize the vocals and thus separate it from the accompaniment. And also for SATB or soprano, alto, tenor, bass, choral singing, in which case we separate the different voices, soprano, alto, tenor, and bass from a choral mixture. So in the first case, we have, most of contemporary popular music involves some vocals which have been processed. Now there are several different techniques for processing the vocals, but some initial ones could just be distortion or reverb, or even more complex ones like wah effects. But in any case, when these are mixed with the accompaniment, the time frequency masking technique, which is typically used in deep learning, is only able to separate the processed vocals from the musical mixture. What we proposed was using voice synthesis to do the separation, well, combining voice synthesis techniques, which are also gaining popularity with deep learning, to do the separation. To do this, we would extract the linguistic content, the melody, and the timbre from the musical mixture, and use these to generate vocoder features, which could be used to generate the singing voice signal, the clean singing voice signal. This is okay. So the linguistic content basically refers to the content which is being spoken by me, which is sort of universally understood. And if I were to transcribe the linguistic content for two different people saying the same, reading the same passage, then it would be the same, even though the timbre or the melody might be slightly different. And this is what we use in conjunction with vocoder features, which I guess are also gaining a lot of popularity in the recent few years with deep learning, which we can think of now as just a compressed representation of the voice signals. So the framework that we used was the voice conversion algorithms, which have also been getting highlight in the last few years, are used to generate a sort of language independent linguistic content. And we combine this linguistic content along with the F0 estimation algorithms and singer uh, identity representation to generate vocoder features, and thereby synthesizing the clean vocals. So such separation via synthesis, as we call it, can be used for analysis of and transcription of vocals with effects, for enhanced and active listening, for teaching applications, and even restoration of old or damaged recordings. The presentation I did earlier in this group, which Paulina was referring to, I've actually presented this same work before, but just to recap. The second part of the thesis was on SATV ensemble singing and source separation between these. So, well, there are four voices in a SATV choir. So we all know soprano, alto, tenor, and bass, and these have their distinct vocal ranges. And singers are generally assigned to a group based on the range that they're comfortable in. But within a single voice, usually we'll have multiple singers, singing the same melody and the same content simultaneously, and this is known as a unison. So the first idea is to separate the different voices, the different parts, soprano, alto, and tenor bass, even though they are unison from the choral mixture. And for this, we sort of tested some of the state-of-the-art source separation algorithms proposed both for musical source separation and speech source separation, as well as in the spectral domain and the waveform domain. And we found out that, well, for now, musical source separation algorithms at least function uh, are more better suited to source separation algorithms such as the contrast net, which were proposed for speech source separation. Using this, the two frameworks, let's say, we presented a complete framework for choir resynthesis, in which case we have a multi-singer choral recording, which can be separated into the unison signals for the soprano, alto, tenor, and bass, from which we estimate content, apply transformations, and can resynthesize single singer singing the individual parts, which can again be multiplied to a unison and remixed to um, create a multi-single choral recording, which can be transposed up and down, or which can be time shifted and used for training the listening purposes. Maybe I can share an example. I'm not sure if you can hear this.
No, not really.
Okay.
Have you shared the sound?
I am not sure how.
Do you want to reshare?
I can share sound. Okay. So maybe I'll play this just from the beginning.
Yeah.
So this is a choral recording of the song Niño Dios te amore, and I guess this is from the choral singing data set, which has recently been released. And what we do is use the system to separate the individual tracks and synthesize them, semitone up and semitone down, and resynthesize. So this is the same song passed through the system and transposed the semitone up. So these were the two remixes transposed up and down. Of course, there are still some errors which there are errors which are propagated in the source separation stage, which get transmitted and further degraded in the individual stages. But I believe with some further work, the framework could be improved and could be used for practical teaching purposes. So some conclusions from the thesis: we have a component agnostic framework for source separation via synthesis. Singing voice system was also presented, and we so some initial foray into source separation for ensemble singing, and a framework for unison to solo and solo to unison synthesis. And all proposed methodologies are available as open source repositories with uh, code and pre-trained models. I guess you can check my GitHub page for those, or also they're present with the thesis. So during this, I guess in March, I joined a company called VoiceMode, which is also here in Spain, in Valencia, and they have a product called the Voice Changer, in which there are real-time voice changes. So if you're using this product and using Zoom, we can add some effects. There are different effects, some different voices which can be added, as well as created. You can add chain up different effects to create a single voice that you would like to sound as, and also a soundboard where different sounds can be triggered while in a call, or more importantly, as we'll see later, as the product is used mostly by gamers and content creators, so they like to use this stuff more. Um, the technology is we have ultra low latency, so the work changes, even though they're on the net, can be done through in real time. And we are releasing real time voice changers to actually allow you a voice to be converted from one voice to another. Well, I guess the idea behind the company is to allow everyone to be heard. Well, especially considering the metaverse that we all seem to be headed towards. It's to allow all humans to be able to communicate through sound and be heard in the way that they want to be heard. Those are some lofty goals, and we're sort of moving towards those. But for now, we just have social online gamers as well as content creators who are the biggest users of the VoiceMode product. I believe there are around 5 million monthly active users currently, and the company is hoping to go towards 100 million users within the next 2 or 3 years. And of course, due to the pandemic, this sort of usage has been amplified a bit. But for us, the more interesting part is on the research. So we are doing a lot of research on real-time voice conversion, speech enhancement. It says text to speech, but it actually should be text to speech synthesis, as well as singing voice synthesis, bandwidth extension, and voice parameterization. So one of the things that I've been working on, because this was also a big part of the PhD thesis that I was doing, is real-time voice conversion, wherein speech by one speaker is converted to speech by another speaker, while the content between the two voice signals remains the same. It should be perceived that while the content is the same, it should be perceived that the speech is coming from the target speaker, but not the input speaker. There have been around 100. It has received a lot of interest, this topic of voice conversion, and there have been around 100 different models proposed over the last 2 years alone. And most of them follow a structure wherein there's an input voice, which is usually compressed into an input representation, such as Mel spectrogram or MFCCs, from which a process known as disentanglement is applied. This can be in many shape forms, such as vector quantization or GAN-based cyclic losses, or even distillation from automatic speech recognition systems to create the linguistic content, which, along with a target speaker representation and FNES, fundamental frequency or loudness estimation, is concatenated and passed through a decoder, which typically generates vocoder features. So vocoder features, again, as we discussed earlier, are sort of a compact representation of the speech signal, and these are used to generate an output voice. So by changing the target speaker, we can effectively change the target or the perceived target of the voice, which is synthesized in the output. So in the case of internal voice mod, we have developed a system which uses both MFCCs and Mel scale spectrogram, along with a dilation network using ASR. This is used to disentangle speaker-independent linguistic content, as well as timbre and prosody, and along with a target speaker identity with a one hot vector. This is passed through a decoder to generate synthesis parameters, which in this case we use the modified DDSP. The DDSP, as you know, is the differential digital signal processing parameters model. We have modified it a bit to work with speech, and this is used to generate the synthesized sound sample. But the problem here, as well as in the thesis, and this is the one which I'm most interested in right now, is of evaluation. How to evaluate a speech sample which has been generated. So, as you know, we thought of 7 criteria, including the quality of the audio, the naturalness of the speech. So audio quality and naturalness, you might think they sound similar, but actually the quality of a voice, let's say taking the classic example of a Darth Vader in the Star Wars franchise, you can say that the quality of the voice is good, even though it's not natural. So that's the distinguishing criteria between these. Then the intelligibility, can you actually understand the content? Retention of the content is similarity of content between the input and the output. This should be same. Similarity of the target to target, in that the audio sample should be of the output should be more similar to the target speaker than to the input signal. as well as robustness to noise and degradations. And of course, we want this to be working in real time. So we want to test real time capabilities. So this is again a topic that I was interested in during the thesis, but objective evaluation is needed because during the thesis I mostly did subjective evaluation in which listening tests involving opinions from a lot of people are needed, and it's always hard to get this opinion. So over the last few years, a lot of metrics for objective evaluation of speech signals have been proposed, including BISCOL, or WarpQ, PESC, NVPESC, and so these are intrusive metrics which require a reference signal and an output signal to be compared. Other metrics include the NISCA or MOSNet or MBNet, which have been proposed, which just provide a prediction on the quality or naturalness based on just the reference signal just the output signal, and do not require a reference to be compared to. So what we want to do in the next few months is, well, to evaluate over 100 voice conversion models, which we have identified, and also the five components. Well, the five components being the input representation, the disentanglement, the target representation, the decoder, and the vocoder, and evaluate all such models, and hopefully run listening tests where we can sort of validate the metrics. So to do that, we have been developing a evaluation framework, which is capable of carrying out multiple inferences of audio based on Docker images. So if we have a model which can be used for generating voice or any audio, it can be passed through this model, this evaluation framework using a Docker image. And for now, we calculate objective metrics for each inference, doing resynthesis of the same signal, conversion to a male voice, conversion to a female voice, and hopefully um, well, later we will use this listening test with the mean opinion score, and hopefully we also plan to run some sort of linear regression or non-linear regression to get some sort of mapping between the output of the various metrics and the subjective mean opinion score. And hopefully we plan to release our results and the evaluation framework to the community for benchmarking um, soon, hopefully next year, as that's the plan. And well, I guess we are also sort of hiring. VoiceMode is hiring, so if anyone is interested, they can please contact me. And yeah, I guess that's all I have for now. Thank you.